2016 AMC12A Question 14. Each vertex of a cube is to be labeled with an integer from 1 through 8, with each integer being used once, in such a way that the sum of the four numbers of the vertices of a face is the same for each face. Arrangements that can be obtained from each other through rotations of the cube are considered to be the same. How many different arrangements are possible? So what's happening is this. We have a cube with its 8 vertices in these locations, and we're numbering them with the integers 1 through 8, not repeating anything, and I want the sum of the top 4 to equal the sum of the bottom 4, to equal the sum of the back 4, to equal the sum of the front 4, to equal the sum of the left 4, to equal the sum of the right 4. So the first thing we notice is this. If I sum up all of the numbers from 1 to 8, I will get 36. And if I want the top and the bottom of face to be equal, then the sum for each face should be half of that, 18. The next part, which is something that I did differently than the solution I looked up, I just assumed that the extreme case 1 and 8 had to be adjacent. But here's a better explanation for it that I found on Art of Problem Solving. So if we consider opposite edges, for instance this edge to that edge where they don't share a face, and this yellow edge to this yellow edge, opposite edges must have an equal sum. The reason is this. If this edge has a sum, let's call it 10, then this yellow must have a sum of 8, so 10 plus 8 is 18. If this yellow has a sum of 8 and it's on the same face as this blue, this one must have 10. The opposites must have the same sum because they add up to a third number to get the same sum. So opposite edges have equal sums. And so here's what they did to say that 1 and 8 have to be on or adjacent. If we assume that 1 and 8 are not adjacent, so let's say 1 is right here and 8 is down there, that lets me know that 1 plus some value must equal 8 plus some other value. But this has no solution in the set from 2 up to 7. For instance, 1 plus the largest remaining number, 7, is 8, and 8 plus the smallest remaining number, 2, is 10. I can't possibly make this one big enough and or this one small enough to make them equal, so this means that 1 and 8 must be adjacent. This also tells us that each edge sum must equal 9. So if the 1 and 8 are here, that's 9. That means that this must be 9, and to add up to 18, this must add up to 9, this must add up to 9. And the ways we get that are 1 and 8, 2 and 7, 3 and 6, and 4 and 5. Next thing, if I just took this straight away and did 1, 8, 2, 7, 3, 6, 4, 5, the horizontal top and bottom and the vertical left and right faces will add up to 18, but the back and front will not, because I'll do 1 plus 2 plus 3 plus 4, which is 10, and 8 plus 7 plus 6 plus 5, which should be 26. So this doesn't work, but if I keep 1, 8, this order, and do this, the way that I can switch these around is 1, 8, 7, 2, 6, 3, and 4, 5. This choice of flipping or not flipping is the only way to get each of these to add up to 18 as well. So let me put it on here so you can see what I'm talking about. If I put 1, 8, 7, 2, 6, 3, 4, 5, if you add up each face, you will get 18. Now I'm not going to consider 8, 1 because 8, 1 is the same as just, flipping one edge. It's actually going to give me a rotation. So I'm going to fix this as 1, 8. And after all this work, it just breaks down to the following argument. How many ways, throwing out the ones over rotation, can I move these on a square with 4 vertices? And that can be found by 4 factorial for permuting each of these around, divided by 4 for getting rid of the 4 different rotations, where I go 1, 7, 6, 4, or I go 7, 6, 4, 1, or I go 6, 4, 1, 7, or I go 4, 1, 7, 6. Those are the 4 rotations. And that's going to give me 6. So there are 6 total ways to assign numbers to the vertices of this cube so that the face sums are all equal. Feel free to comment below with any questions.